Hey guys, started chapter 7. So this is what we have for normality. So the normal probability distribution and what it entails. So this is section 1, properties of the normal distribution. So we're only going to cover the first 2 sections of this chapter. So use the uniform probability distribution. So imagine that a friend of yours is always late. Let the random variable x represent the time from when you are supposed to meet your friend until he shows up. Suppose your friend could be on time, so that would be x equaling 0, or up to 30 minutes late, so x equaling 30, with all equal intervals of time between 0 and 30 being equally likely to happen. So for example, your friend is just as likely to be 3 to 4 minutes late as he is to be 25 to 26 minutes late. The random variable x can be any value in the interval from 0 to 30, that is 0 less than or equal to x less than or equal to 30, because any two intervals of equal length between 0 and 30 inclusively are equally likely to happen. The random variable x is set to follow a uniform probability distribution. And so you guys could see what that looks like. It just looks like this. It's really boring. I honestly don't know exactly why they went about it this way. There's a bunch of other ways that they could have kind of explained this in a better way, but coming over here, probability density function is an equation used to compute the probabilities of the continuous random variables. It must satisfy the following 2 properties. 1, the total area under the graph of the equation overall must be equal to 1. Over all possible values of the random variable must be equal to 1. The height of the graph of the equation must be greater than or equal to 0 for all of the possible values of the random variable. This is what they came up with. Doesn't really follow a normal distribution. It just shows what a uniform distribution looks like. And here, these are very boring because there isn't any sort of variability. Everything is equally likely to happen. So it's like a perfect situation that you can't really do much math with. Like it's kind of sucks. But let's, so the graph below illustrates the properties for the late example. And notice that the area of the rectangle is 1. Area as in like length times width. So 1 over 30 times 30 gives us 1. What else? Notice that the area of the rectangle is 1 and the graph is greater than or equal to 0 for all values of x between 0 and 30 inclusively. Because the area of the rectangle is height times width. Width of the rectangle is 30, height must be 1 over 30. So that's how they got these values. Again, this isn't what you're going to be tested on or anything, so you don't have to worry about that too much. But now this leads us to the area under the graph of a density function over an interval represents the probability of observing the value of that random variable. So if we, so kind of going along how they presented this material, we have our graph. We could say that this is our graph. So if we're looking at the area between one value here and another value, say over here, us finding this area in here, the area represents the probability. We could say like A to B. So the probability of A being less than or equal to X, less than or equal to B. So that would be the probability. That's all they're kind of saying here or stating here in this part right there. Next, refer to the situation in the previous example. What is the probability that your friend will be between 10 and 20 minutes late? So between 10 and 20 minutes, there are 10 minutes there. So we're looking at 10 divided by 30. So that would be 1 over 3. And the way that we could kind of see that, the way I came up with that so quickly is because we have this area here up to this very edge is 30. Here we have 1 over 30. So the probability of being 0 minutes late is 1 over 30. The probability of being 10 minutes late is going to be here. The probability of being 20 minutes late is going to be here. So looking at these values here, what we could do is look at this entire area up to 20. So this entire area, because we have 20 minutes by 1/30th of a minute, we would have 20 over 30 minutes. But since we grabbed too much data, like we didn't need this entire first block here that was judging up to 10 minutes, we know that this is 10 over 30. So the actual computation is going to be just that. The entirety from 0 to 20 minutes minus the value of that before it. So 20 minus 10. So remember what we talked about whenever we have two fractions that we're either adding or subtracting. The denominators have to be the same in order for us to add or subtract across the top. And from here we have 20 minus 10 in the numerator. So that's going to be 10. And we keep the same denominator. So 30 at the denominator. And then we could simplify both the top and the bottom. Top is divisible by 10 and the bottom is also divisible by 10. So we would have 1 over 3. So the area is 1 over 3. So the probability that the friend is 10 to 20 minutes late is going to be 1 over 3, or we could say approximately 0.333, because that number keeps repeating itself. All right, awesome. Let's see if they could explain it in a different way. So we want to find the shaded region. The width of the shaded rectangle is 10. So we could say that it's 10. So they went about it a slightly different way, but still kind of like exactly the same. So the width of the shaded rectangle is 10. Height is 1 over 30. So it's going to be 10 over 30, or we could say 1 over 3, or 0.333. So the probability of your friend, the probability your friend is between 10 to 20 minutes late is going to be 1 over 3. Let's see, it's 10 a.m. There is a 20% probability your friend will arrive within the next blank minutes. So how could we say that? So it's 10 a.m. There is a 20% probability that your friend will arrive within the next blank minutes. So probability of blank, or I'm sorry, probability of X being less than or equal to blank is equal to 20%. So 20%, what we're looking at is like the complete opposite. So we're kind of working backwards with this one. So here, what we have to find is the shaded region where the area ends up being 20%. And if you actually look at 20%, the way we could turn this into a decimal is by dividing this value by 100. And by dividing it by 100, we get 0.2. And 0.2 is the area that we're looking for. So when we find this, the area here is going to be 0.2, which is a probability that, like, we're kind of just working backwards. So first we needed a area. This time we have an area that we're given a time, that we need a time for. So we're kind of working backwards. So the area of the shaded region in figure B is going to be 0.2. So here we need to determine the width. So here, instead of finding that value, we have the entirety of 30, and we're just going to multiply it by the value of the percent. So 30 times 20%, or 30 times 0.2 gives us 6. So there's a 20% chance that he would be here within the next 6 minutes. So again, 20% chance that he would be here within the next 6 minutes. And we got that from this computation right here. So again, there is a 20% probability that your friend will arrive within the next 6 minutes, or by 10:06. All right, so next we're going to talk about the graph of a normal curve. So just like we were talking about in the previous video, something that's normally distributed is going to have like a normal shape like this, roughly. So in mathematics, a model is an equation So a model is an equation, table, or graph used to describe the reality. So the red curve, you could barely see it. Let's try to make these a little bit darker. So the red curve, there's 1, 2. These are very roughly drawn. All right, 3. So those red curves. So the red curve in the figures is a model called the normal curve, which is used to describe continuous random variables that are said to be normally distributed. So these are examples of normally distributed data. Some of them are going to be roughly distributed, so it's not going to be exactly, like values aren't going to fall in exactly within these curves. So we just call them roughly normal. So roughly normally distributed. A continuous random variable is normally distributed or has normal probability distribution if its relative frequency histogram has the shape of a normal curve. So remember, histograms look just like this, where the area where each graph or each bar is touching the one right next to it, if there are any values there. There we go. So it's going to take on values that look like this. We have 2 inflection points. And if you guys have taken calculus, you would know that an inflection point kind of changes concavity. So it goes from concave up to concave down. But for this class, inflection points are just the areas where they're changing. So increasing at an increasing rate or increasing at a decreasing rate. So we're looking at values like that. So roughly these 2 spots right there and right there, those are inflection points, and they're found within 1 standard deviation from the mean. So remember, this line right here in the middle is going to be the mean. 1 standard deviation to the left is going to be your first inflection point. 1 standard deviation to the right is going to be your other inflection point. Let's see, points at x equaling the mean minus our standard deviation and the mean plus our standard deviation are the inflection points on a normal curve. So the points on those on that curve where the curvature of the graph changes. So notice that we're kind of concave up right here, concave up. So if we put like water or something into this glass, it would fall there. And similarly, if we look at this value here, if we blow little particles of air up this way, it's all going to kind of fall into these values right here. So kind of looking at those values right there. Concave up, concave down. All right. The figure shows how changes in mean and standard deviation change the position or the shape of the normal curve. So in figure A, increasing the mean from 0 to 3 caused the graph to shift 3 units. So the mean right here, remember the mean is where we find our highest point on the graph. Same thing over here. If we were to change the mean, we increase the mean, we're shifting everything to the right. Decreasing the mean would shift everything to the left. But now what changes in figure B, increasing the standard deviation from 1 to 2 caused the graph to become flatter. So increasing it from 1 to 2. So with standard deviation 2, here in the mean, looking at the mean for both of these graphs, even down here, this one here, looking at the mean is not changing whatsoever. So we're not shifting the graph from left to right. Now it's taking twice as long to get to your inflection points. So here are the new inflection points. These are where the old inflection points were right here. Increasing the standard deviation kind of pushed the graph down from the top. So kind of just imagine you putting your flat hand over that graph and just kind of pushing it down until the standard deviation became 2 in this case. All right, so now state the properties of a normal curve. So properties of a normal density curve. So 1, it is symmetric about the mean, because the mean is equal to the median, which is equal to the mode. The curve has a single peak, and the highest point occurs at x equaling mu. it has inflection points at 1 standard deviation from the mean. So 1 standard deviation below the mean and 1 standard deviation above the mean. The area under the curve is 1. The area under the curve to the right of the mean equals the area under the curve to the left of the mean. Let's see if we actually have a picture. There we go. So what they meant from that is we have the area under the curve to the left of the mean. This area over here is equal to the same thing on the opposite side. So this area over here. So the area to the left, which is the area in red, is equal to the area to the right of the mean, which is the area in blue. And that happens because we're all exactly symmetrical here. All right. Next, as x increases without bound gets larger and larger, the graph approaches but never reaches the horizontal axis. And as x decreases without bound, the more and more negative you go, the graph approaches but never reaches the horizontal axis. So coming over here. So looking at this data right here, as we keep going further and further left, I wish I could zoom in, but as we go further and further left over here, we get really, really close. So I'm just going to kind of extend this. We get really, really close to that line, but we never touch it. So we could keep zooming in and zooming in and zooming in on a normal distribution. It's never going to touch 0. It looks like it is going to touch 0, but it never does. So it does that all the way to the left of the data set, all the way to the right of the data set. We get closer and closer to 0, but we never touch it. And by 0, I mean this. So we have like our graph along this line right here. And let's just pretend that that's a straight line there. So it's a graph along that line there. So 0 as y, I'm kind of looking at our y-axis. We get really, really close to 0, really, really close to this horizontal line right here. That's the value of y equaling 0, or our height equaling 0. So as we get closer and closer to infinity, we get closer to 0, but it never ever crosses. Oh, let's go backwards. All right, lastly, the empirical rule. Ooh, I spelled empirical rule wrong in the previous video, so I apologize about that. But I did warn you guys, I'm a math professor, not an English professor, so my spelling is going to be incorrect a lot of the times. Really, really apologize about that. All right, so the empirical rule, not empirical. So sorry, not an I, but an E. So the empirical rule, approximately 68% of the data under the normal curve is between the mean, or is within 1 standard deviation of the mean. Approximately 95% of the data, or approximately 95 of the area, is between 2 standard deviations of the mean. And approximately 99.7% of the data is within 3 standard deviations of the mean. And what they're talking about is this right here. So this looks really familiar. We would have seen that, or we saw this in chapter 3, I believe the second section, or the section where we talk about measures of central tendencies. I believe it was one of those sections. And this is what they're talking about here. So we have 68% of the data within 1 standard deviation. And we could actually find these values here, not in this section, but in the next section, I believe. But here we have these. So within 68% of the data, 99% of the data within 2 standard deviations, 99.7% of the data within 3 standard deviations. And that's why whenever we say that it's more than 3 standard deviations, it's unusual. Technically, after 2 standard deviations, depending on how you word things, within 2 standard, anything more than 2 standard deviations from the mean is going to be abnormal. Abnormal or unusual. Explain the role of an area in a normal density function. Okay, so looking at this, the relative frequency distribution given in table 1 represents the heights of pedestrians 3 years old, pedestrians 3-year-old female patients. The raw data indicate that the mean height of the patient is 38.72 inches with a standard deviation of 3.17. So looking at this data here, we could graph some of these. So they said that the mean was 38.7 or 38.72. Standard deviation is 3.17. So here, drawing our beautiful normal curve. Here, the mean is always going to be the middle because that's where majority of the data is. It's going to be at the highest point of our graph as well. So here the mean, they gave us the mean of 38.72. So we would have 38.72. And let's take it over to Excel so we could make Excel do some of the work for us. And I forgot what these were. So they said that the mean is equal to 38.72. The standard deviation, 3.17. Okay, so now within one standard deviation, we're going to subtract our standard deviation and we're going to add our standard deviation for those two parts. So we have 38.72. And we have 3.17. And we're adding and subtracting 1. So this is going to be equal to this minus this. And that's going to be 35.55. And we're going to add it. So we're just going to keep the same one. So plus. And over here on this side, it's going to be 41.89. And that's one standard deviation away. So what we could say, pretending that I drew this nicely. So we could say that 68% of the data is going to fall between 35.55, 41.89. And now let's see what 2 standard deviations away is. So 2 standard deviations is going to be over here. So we could multiply this value by 2, multiplying the standard deviation by 2. This is plus, you can see the plus right here. So adding it, that was 45.06, 45.06. And you could do this with a regular calculator as well. So this part, these computations aren't too crazy. You could do it on a regular scientific or even your phone calculator. 2 standard deviations below the mean. So below is minus. So instead of plus, we put minus. That's 32.8 or 32.38. And within 2 standard deviations, we're looking at 95% of our data. And the last one, 3 standard deviations. So we're just going to plug a 3. Instead of multiplying our standard deviation by 2, we're going to multiply it by 3. And since it's minus, it's going to be below. So this is 29.21. And plus, this is 48.23. And here within 3 standard deviations from our mean, we have 99.7% of our data. So 99.7% of our data falls within 3 standard deviations of the mean. And that's all they wanted to say. So just to kind of look at this, we would say that about 99.7% of our data fall between within 99%, that's 3 standard deviations. So that's these in red right here, 29.21 and 48.23. Put too many ends. And that's it there. Let's clear this out and see if we missed anything. So draw a relative frequency here. Draw the normal curve. We drew the normal curve on top of it. Oh, I see what we did. So they did something a little bit different. So they actually they graphed these values here first. It will be a little bit too difficult to kind of throw it onto Excel. And I'm not saying difficult, just saying that we would have to find like the midpoint between these values and then graph the relative frequency. But we could see that they did that for us here. They graphed it for us. And from here, they drew the reflection point. They saw the inflection points and they kind of just drew 2 standard deviations left, 2 standard deviations right, or in this case, 3 standard deviations left, 3 standard deviations right. And their graph roughly looks like what we have drawn here. So they went 3 standard deviations and we got 29.21. 29.21 is about here-ish. That's 3 standard deviations away from the mean. This also shows a rectangle whose area represents a proportion of 3-year-olds between 40 and 40.9 inches. So notice that the area of that shaded region is very close to the area of the normal curve. And the reason say that it's really close is because the midpoint between these two is right here. And that's how they drew those values out. Next, the equation or model used to determine the probability of a continuous random variable is called the probability density function. The normal probability density function is given by this. So y is equal to 1 over the standard deviation times the square root of 2 pi times, like we could graph these values right here. They would be kind of crazy, but we could still graph this, and this is going to give us a normal distribution. This isn't anything that you're going to be tested on whatsoever. This is kind of like university level or higher statistics classes, like an advanced statistics is where you would kind of learn how to play around with this stuff here. But they kind of just wanted to show you what these would look like. And then they would say where mu is the mean and sigma is the standard deviation of the normal random variable. So don't feel threatened by this equation because we will not be using this in the text. Instead, we will be using the normal distribution in graphical form by drawing the normal curve. So I'm sorry that they threw this in here. Kind of just scares us a little bit, but it's okay. Area under the normal curve. So suppose that a random variable x is normally distributed with the mean, mu, standard deviation, sigma. The area under the normal curve for any interval of values of the random variable x represent either the proportion of the population with the characteristic describing the interval or the probability. So the probability that the randomly selected individual from the population will have those characteristics described by the interval of the values. So whenever we find a value, whenever we find the area under the curve, it could mean either one of these. It could either be the proportion of the population, blah, 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 or it could be the probability of blah, blah, blah. So proportion of people, what was one of the examples they kept using? So proportion of people who who would rather give up chocolate than to give up their cell phones, or the probability of people who would rather give up chocolate than to give up their cell phones, or whatever example they used in the previous chapter. So those are the 2 different possibilities that we could have when looking at the area. It all seems a little weird until we actually look at these values. All right, so the serum total cholesterol for males 20 to 29 years old is approximately normally distributed with a mean of 180 and a standard deviation of 39.2 based on the data obtained from the National Health and Nutrition Examination Survey. So it kind of looks like those 2 are going to be important. So let's take it down. So the mean is equal to 180. The standard deviation is equal to 36.2. A, draw the normal curve with the parameters labeled. Don't worry, we got this. So let's draw our normal curve. Doesn't really look normal. Better. So that's our normal curve. Remember, the mean is always going to be here at the middle at the highest point of our graph. The mean is going to be 180. So from here, we're going to add 180 and subtract 180 a couple of times. So the mean and the standard deviation. Mean is 180, standard deviation 36.2. And we have those values there. And to go one standard deviation below, we're going to subtract the 36.2. So this is going to be equal to 180. So 180 minus 36.2. So one standard deviation is going to be 43. So 143.8. And adding it. To 16.2. And for the sake of this problem, let's just go out what are 2 standard deviations. So 2 times. So going out 2 standard deviations on the left side, 252.4. And going to, oh, that should be over here, 252.4. And subtracting it, 107.6. So we went out 2 standard deviations. So remember, 1 standard deviation is going to be about 68% of the data. 2 standard deviations is going to be 95% of the data. That's why I only wanted to go out 2 standard deviations, because I don't even think that they would go. Yep, they only went out 1 standard deviation. So we even went a little bit above and beyond what they wanted us to do. So draw a normal curve with the parameters labeled. So here they went out 1 standard deviation. Remember, these are called our inflection points. Also remember, 68% of our data lie within 1 standard deviation of the mean. So we subtracted 1 standard deviation, got this value, added 1 standard deviation to the mean, got this value over here. And now that we have that, so an individual with a total cholesterol greater than 200 milligrams per deciliter is considered to have high cholesterol. Shade the region under the normal curve to the right of 200 milligrams per deciliter. All right, looking at this here. So notice that 1 standard deviation is over here. So we have 80 to 16, about somewhere here in the middle is going to be those areas. So about 200 is going to be right here. One more time, shade the region under the normal curve to the right of 200. So to the right of 200 is going to be this shaded region right here. So to the right of 200 is going to be that. And let's kind of see what that interpretation is. So one more time, an individual whose total cholesterol greater than 200 milligrams per deciliter is considered to have high cholesterol. We would say that these people here have high cholesterol. So have high cholesterol. And let's see what they say. All right, so they shaded that region there. And lastly, suppose the area under the normal curve to the right of 200 is 0.2903. So here we're saying that those values are cholesterol levels. The area here is also 0.2903. And you will learn how to find this area in a later section. Of course, we will provide 2 interpretations of the results. So I kind of don't want to physically write everything, so we'll put it over here. 2 interpretations. So we could say the proportion of people with high cholesterol is approximately 0.2903. So we have that. So the proportion of people with high cholesterol is approximately 0.2903. And if we were to select at random a person in this population, there is a 0.2903 probability that this person has high cholesterol. So remember, whenever we have that area represents two different things. So depending on how the question is stated, this either represents the proportion of individuals in the population of like state claim, or it represents the probability that we would state the claim, and then we would say the probability. So in this case, the probability of high cholesterol is 0.2903, or the proportion of people with high cholesterol in this population is 0.2903. Clear this and let's see. Oh, and there we go. That's it. So that's a way that we could interpret these results. If you guys have any questions, please email me. But if not, good luck, guys. Bye.